You guys, and this is relatively true if you look in my backyard. In the wintertime, you can see it because the snow melts on one side of my yard but not the other because of where the fence line is. Like you can see the shadow of the fence with which snow melts and which snow doesn't, right? And there are so on one side the grass grows just like out of control, and on the other side the grass barely grows at all. You guys get what I'm saying there? It grows, but it doesn't need mowed, whereas one side needs mowed all the time. Cool? So I want you to think about what if we went into my yard, we picked up every single blade of grass in the middle of July, when grass grows a lot. And we all measured the height of the grass in my yard. You with me? And I haven't mowed yet. What would we expect that picture to look like? Would it be random? Okay, what if I were to tell you the sunny side is huge compared to the shady side? We would expect a lot of really tall grass, right? And kind of work its way down to some short grass. Everybody good? So like here would be tall and here would be short. And we would use like numbers to describe these, right? And we'd have some in the middle that kind of, and in fact it actually ends up kind of fading up, right? Because the sun moves a little bit during the day. So the majority of my grass is tall with some short. So this would be an example of something that could be skewed left. Everybody good so far? And could I draw a histogram that kind of describes this? And let's say that we made the height of each bar in my histogram the probability that it occurs, that bar occurs. Is everybody with me? What should the total of the probabilities in the histogram be? 100%, right? And because of that, here's what kind of happens. The sum of the histograms, or the sum of the bars of the histogram would equal 1. Because they should totally add up to 100%. Is everybody good? Now, it turns out that what we like to do for continuous variables is create kind of a curve that summarizes it. Okay? You guys have dealt with curves that summarize this before, you just didn't realize it. The normal distribution is a curve that summarizes an approximation of a continuous variable. Okay? All right. And so when we have those curves, like for instance, this blue line is summarizing each of these, right? Okay. The area underneath the curve, kind of, is 1. For the same reason that the sum of all those bins equals 1. Everybody good so far? Now. Oh. So, all right. Now, you guys, the next thing I want to point out. Can a blade of grass be exactly 2 inches long?
Surely not.
Well, where are you going from the roots?
It could be, yeah.
No matter where we're going from, is it exactly 2 inches long?
Like a 0.0005% chance that
It's I bet it's actually way lower than that, right? Because if I tried to cut a blade of grass to be exactly 2 inches and then I used a different measuring device that was more precise, it wouldn't be exactly 2 inches. Are we comfortable with this idea? It might be 2.003 inches or 1.99992 inches. Do you guys see what I'm saying now? Okay. So last week, the difference between x is greater than 3 and x is greater than or equal to 3 mattered. because there's a big difference when it's a discrete variable. Greater than 3 has a different meaning than greater than or equal to 3. Do you guys see what I'm saying here? When it's a continuous variable, it does not matter. So if I say greater than 2 or greater than or equal to 2, it does not matter. Well, it isn't. Okay, so in order to for continuous variables, if we want to find a probability, we find the area under the curve. And so what happens is, what we're going to end up doing to find these, the way we end up calculating it, you won't even be thinking about, do I include the number or not? For the discrete, you will. For the continuous, you won't even be thinking about it. It won't be a big deal. Okay? Let's look at, so today we're only going to focus on one type of continuous random variable, the uniform random variable. Okay? So let's go ahead and say that the heights of trees in a certain area are uniformly distributed between 12 feet and 17 feet. What is the probability that a tree is less than 14 feet in height? Okay, you guys, what does uniformly distributed mean? That each height of tree has about the same probability. Is everybody with me? So as we start to draw, if I wanted to draw a histogram of this might be 12, this might be 17. And that histogram would be straight across. Flat top. Now, for uniform distributions, the histogram and the curve that we were talking about are pretty much the same thing because the histogram is nice and rectangular, yeah? Okay. And what did we say the area under the curve always is? 1. Is everybody with me? So could we figure out the height of this rectangle? What is it?
Oh, but you can figure it out.
How are you getting there? Get there.
There's 5 in between 12 and...
So the base of the rectangle is 5, yeah? And base times height is how we find the area of a rectangle, so it would have to be 0.2. And some other ways we might think about that. If that is not feeling great to you, that's okay, because that's a pretty weird way to think about it.
Wait.
If I turn this into a histogram, each one being 1 unit wide, so this would be 13, 14, 15, 16, yeah, 17. One guy. And I said, what's the probability you're in this box? These are all equally wide, right? 1 out of 5 areas. Is this okay? All right. So, if I gave you this, you guys, what is the probability that I randomly select a tree that is less than 14 feet in height? How are you getting that? Okay. So we might start looking at this as, are you guys with me? We just talked about it being an area. We're essentially trying to find this orange area. Does that make some sense? And we could say, hey, this distance is 2. This distance is 0.2. That's equal to 0.4. Everybody good?
I know you explained
Because
right, that
5 by what would give me 1?
okay. I did it a different way that might be easier because my brain understands the way better.
Go ahead.
They all add up to 100% or 1, and then that divided by 5 is 20%.
So that's, you split it up every 1 foot of.
So technically this is the x is 0.5.
The x is the tree height.
Or the y. I'm confusing myself. No, never mind.
I'm gonna work some more examples with this and that I think might help. Okay, you guys, and when my picture looks like this is not a problem. Now, what if instead I wanted to find a tree that is between 11.5 and 15 feet tall? Wait, you guys, I mean 12.5. 11.5, there isn't. Shoot. And I'm going to do this area in pink. So 11.5 or 12.5 would be roughly here to 15. And so as we start doing fractional hours, maybe this starts to feel a little bit icky. Is this okay? But sometimes we think about probabilities as like the desired part over the total, yes? And when it's just a rectangle, when it's uniform, it's almost like we have between here to here. Do you guys get what I'm saying there? Okay? So it's almost like we can think of this as doing, well, how far is it between 15 and 12.5 out of how far is it total? So the distance of the range you're trying to find the probability of over the total distance of the distribution. And then it's pretty easy to see that this is equal to 0.5.
Can you say what the two rows were again?
This would be the distance of the range. The distance of the event, right? So that would be the between 12.5 and 15. And this is the total distance. You guys, this is not on your formula sheet.
Maybe you just do it, like each box is 0.2, so then half of that box is 0.2.
Sure, but if I said between 17.35 and 16.22, like, so the idea is you can always do this.
So you can only do this one, the fraction one, when it's between two numbers?
Well, we could have done this one. The only difference would be we'd have to recognize then, oh wait, that's between 12 and 14. So to be less than 14 would be between 12 and 14. All right, let's look at this next one. Suppose the package delivery times are uniformly distributed between 4:30 and 3 p.m. I said that backwards. You guys, what is the distance between 3 p.m. and 4:30 p.m.?
90 minutes.
I'm going to leave it as 90 minutes, but we could have said an hour and a half as well, which someone whispered. Okay, everybody good? All right, and then this is what we're trying to find the probability of, the after 4:14 p.m. How many minutes are after 4:14 p.m. in this model? So if I want to, So if I want to find the probability that something's going to be delivered in those 16 minutes, I would do 16 out of 90.
What do you think it is? Do you already know?
It'd be 8 out of 45, which is really close to a little bit bigger than 8 out of 48, which is 0.16 repeating, so 18%. Oh, I was muted. And then 0.8 over 2 is 0.4. Or 40% likelihood.
So you can, I think you said this, you can only do this little.
Only when it's uniformly distributed. That's all I got for today. Tomorrow